The topic of this final hour of my presentations is lithium-ion battery fires. And I have a little bit of show and tell. I brought a lithium-ion battery for this. And first, I'd like to say that everything I've presented so far is either from my research or from my teaching. And yet, when I was invited to the summer school, and it's not the kind of invitation that you scratch your head and you think, am I going to accept this offer? They said, we'd like to invite you to come, but we do want you to talk about battery fires. And so I quickly said yes, and then I said, well, how am I going to talk about battery fires? I haven't done research, I haven't done teaching on this, but I do have an excellent colleague, Stas Stoliarov, who has done a lot of research, and he helped me. One way he helped me is with the slides. Another way he helped me is with providing a lithium-ion battery. And so this is what it looks like. And he gave it to me, and then he said, you know what, Peter, be careful when you put it in your bag. Just make sure you don't short out the two terminals. And at the same time, he said, if you short out the terminals, no way, it can't catch fire. But then a few minutes later, he said, just be careful in your luggage. So I also brought with me a AA battery. This is just, out of my drawers. And, people throw this in their luggage all the time, and you don't really worry about shorting these out. First of all, it's hard to make a electrical contact from one end to the other. I suppose if you had a chain necklace or something, you could, but a stack of batteries, it's just impossible to imagine how that could connect. But still, we need to be careful with lithium batteries because they are known to have thermal runaway and to cause accidents. There's an accident shown here on this slide, and if you Google lithium-ion battery fire, you can watch the whole movie. But this is someone, an expert, right? He's repairing cell phones. I don't recall where this is. And the phone he was working on somehow went into thermal runaway and had an explosion, a fireball. And it kind of threw him back. You can see him falling out of his chair. I don't think he was injured, but it's pretty frightening when something like that happens. So for the next little less than an hour, I'm going to talk about lithium-ion battery fires. So lithium ions, they make great batteries. They have a lot of capacity, store a lot of charge, and they can be recharged. Unlike this alkaline battery that, once you use it up, it goes in the waste. Lithium-ion batteries can be charged hundreds of times. So this is a plot of global sales of electric vehicles going up to 2023, and you can see it's like exponential increase. The sales is going through the roof. Everyone wants electric vehicles. I'd like to have an electric vehicle. I think they're great for the environment. And so I'm not alone. It's hard in the United States because it's hard to charge them, but the sales are going up. But what else is going up with the sales is on the next slide, is the number of fires. And look at this. This plot actually is probably a better plot because it shows both the sales as the line, the dotted line, and the fires as the red bars. So they seem to be tracking each other. It's scaled in such a way that it looks directly proportional. The number of fires is directly proportional to the number of sales. So even as we're learning about these batteries and learning about the fire hazard and trying to make them as much safer as we can, we're not making much progress, and we're having more fires than ever before. Now, you also have to factor into this that the car made in 2023 has much better battery performance than the one made 10 years earlier. So we're expecting more out of our batteries. When you buy a cell phone, you want it to be able to have 5 or 8 hours of talk time. You want the battery to last, but you don't want it to last at the expense of fire safety. So let's delve into this fire safety a little bit for the lithium batteries. Here's some advantages and disadvantages of lithium batteries. They have high energy density, although, I did the math on these two, the 18650 lithium battery and the alkaline, and they both have about the same energy density. They have low leakage. So does the alkaline battery. This has a long shelf life. Let's see what the expiration date is on this one. 2033. So this has like a 8-year shelf life. I don't think the lithium-ion battery has an 8-year shelf life, but it does have low self-discharge and high longevity. Lasts for years, can be recharged many times. The disadvantages of a lithium battery are limited operating temperature. You know, when you're charging your phone in your car, sometimes it pops up a message and says, oh, phone's too hot, we're going to stop charging until you get back to normal temperature. So there's a limited operating temperature. Limited charge and discharge rate. People complain with their electric vehicles that it takes too long to charge up, certainly longer than pumping gasoline. And these lithium batteries may be the greatest disadvantage, the one that we're interested in as fire and combustion researchers, are that they're subject to thermal runaway. And so thermal runaway is a condition where the battery starts to get hot, and then even if you stop drawing current or you cool down the outside, it actually heats up all on its own. That's the thermal runaway. There's a lot of energy in these. Even if there's no oxygen, they store a lot of electrical energy and chemical energy, and this can lead to thermal runaway. And usually, if one battery goes into thermal runaway, it will pop and vent all its contents and continue to heat until the point that it ignites its neighbor. And so the neighbor will go into thermal runaway, and these will cascade, and many of the cells can burn. So here's at the bottom a comparison of lead-acid batteries, nickel metal hydride, and lithium-ion batteries, and the energy density. Alkaline batteries aren't shown here, but they're comparable to the lithium-ion batteries. So lithium-ion's 6 times more energy density than lead-acid, and much better than nickel metal hydrides. Here's a comparison of these two batteries. This is a picture of these exact batteries. On the left, the green, this is called a Tenergy 18650 cell. It's a famous name in lithium batteries. It's 18 millimeters in diameter and 65 millimeters long, 18650. And it has all the specifications written right across there. Tenergy, it tells you how many volts, 3.7, how many milliamp hours, how many watt hours. Of course, those 3 numbers there's some redundancy there. You can multiply 2 to get the third one. But it gives you a lot of information. What it doesn't tell you is what's the chemistry inside. What's the cathode? What's the anode? What's the electrolyte? It doesn't really give you that information. It's kind of like just a green-covered battery. And it makes it difficult to do the research because if you buy the same looking battery in 6 months, it could be completely different performance inside. I imagine that you can trust the volts, the milliamp hours, and the watt hours that's shown there, but it's a little difficult to do research on these batteries. It's company specific and proprietary. They really don't want to publish all the details. Okay, so if you compare these two batteries, the 18650 is it's a bigger diameter, a little bit longer, about twice the mass as this AA battery. The voltage is a little more than double, but the capacity, the energy per mass is about the same for these two. The nice thing about the lithium ion is it is rechargeable. So this is the anatomy of a lithium ion battery. For those who are interested, it comes from a great review paper by Nishi, and it shows basically what happens with a lithium battery when it's charging or when it's discharging. So when it's charging, the electrons are going, I guess, in a clockwise direction from the cathode to the anode. When it's discharging, when you're drawing it, for example, to drive your scooter, the electrons will be going in the counterclockwise direction. So the 4 key elements in every lithium-ion battery that are shown here in this sketch, there's the cathode and the anode, and these are separated by that green thing, which is the separator, and it's a polymer. The worst thing that can happen for a battery is that the cathode touches the anode, then you're sure to have thermal runaway. So you need to have a good separator that doesn't conduct electricity, but it has to be able to conduct the ions. And then you have the electrolyte, which includes these lithium salts, and the lithium ions go back and forth between the cathode and the anode, depending whether you're charging or discharging your battery. So there are 4 main components of every lithium-ion battery. They all have these 4 components, but almost, so many different choices of these components. There's the anode in the bold, the cathode, the electrolyte, and the separator. Okay, so almost all the anodes are made out of graphite. Some now they're switching to this lithium compound. when you're not so worried about the energy density. But nowadays, most of them are made out of graphite. The cathode is the other anode, and these are made out of many different types of compounds. I have a slide on this coming up. But notice that these have oxygen. They all have oxygen in them. And the problem here for fire is that when the cathodes get hot, some of that oxygen gets liberated. And that oxygen then can react with the electrolyte, and you have exothermic reactions inside the battery even without any air present. And this can lead to your thermal runaway. The electrolytes are usually organic solvents. These are flammable, and they have those lithium salts. And often they do have fire retardants, but they are usually flammable. And then the last thing is the separator. And this is usually some kind of a polymer. The most common ones are polyethylene, polypropylene. And as I mentioned, it has to be electrical insulator, but permeable to the lithium ions. So they have small holes in it, so lithium ions can actually migrate across. And the thickness is usually 25 microns. So if you only remember one thing from this hour, it's that lithium-ion batteries have 4 main components, and that it stores a lot of electrical energy, but also chemical energy in the form of the oxygen that's in all the cathodes. Okay, so they're made in layers. You know, these layers get you the kind of energy density that you want. In the 18650, they're wrapped around each other so that you get a cylinder. So it's dozens of individual layers all wrapped up together. And you can see that on the picture at the left. That's a cutaway view where you can see, I don't know, what is that, about 20 different wraps of cathode, anode separators in 20 wraps, but sort of shown unwrapped at the top image. Or what we often have in cell phones, because there's not really room for a shape like this in a cell phone, you want something that's more flat. It's called a prismatic cell. This is shown here, where it's not wrapped into a cylinder, but wrapped into more of a flat shape. So often in cars, what's used is cylindrical cells, hundreds or thousands of these 18650s wired up in series and parallel. Often in cell phones and other devices, you have these prismatic cells. But at the core, they all contain the same things: anode, cathode, separator, and electrolyte. So let me first talk about the cathodes. So this is a big table that I drew from a couple of review papers. There are basically 4 main types of cathodes, and they have these abbreviations. As I mentioned, you know, when you buy this, they're not going to tell you which cathode's inside. They'll tell you the operating range, they'll tell you the energy density, the voltage, they'll give you a lot of the parameters that you want if you're designing a scooter, but they're not going to tell you which cathode material it have inside. So the key aspect that I want you to remember is that all of them in their formulas have oxygen. There's O2 in the first one, O4, O2, and another O2. And when that cathode gets hot, the oxygen tends to separate and to come out and can then react with the electrolyte. The uses are shown here, some of the advantages and drawbacks. I guess the main takeaway is in here the uses that the last one, the NCA, is used often for highway vehicles. The NMC is used for a lot of micromobility devices. On our campus, we have dozens of scooters and skateboards and bicycles that probably have this NMC type of cathodes. But from a fire, and then off to the right are some pictures of these. So the top one is a LCO, and this looks like a cell phone, or looks like a laptop battery. The second one down is a LFP. It says Duracell Solar. The third one also is a cylindrical. And the last one, the NCA, this looks like a battery pack and maybe a Tesla with hundreds or even thousands of these 18650s. But at the bottom, I want to show the decomposition chemistry. So two of the most famous common cathodes are the NMC, which liberates, when it decomposes, a half mole of oxygen per mole of cathode material, or the LFPs, which decompose with half as much oxygen. So it turns out that the second chemistry here, the one with the iron, liberates less oxygen, so it's a little bit fire safe, but the manufacturers don't like it as much because there's a trade-off. It doesn't have as good of energy storage capacity. So there are lots of trade-offs in the cathodes, and it's one of the main differences between the different battery types. Okay, another aspect of these batteries, if we start talking, hang on one second. Okay. Lithium-ion batteries, when they go into thermal runaway, they can often have exothermic reactions, so that oxygen that pops off the cathode now is in an organic solvent. It's in some kind of an electrolyte oil, and it's getting at high temperature, so that can react even when the battery's sealed. And very quickly then, you generate, of course, CO2 and H2O at high pressure, high temperature, and the pressure goes up in these batteries. And so they're designed, at least the cylindrical batteries, the 1850s, with safety vents. And I can see here at the top of this battery, four safety vents. Only at one end, at the top end of the battery, there are 4 safety vents. Now, right now they're sealed, but if this starts to overheat and build up pressure, the vents will pop through that vent disc and then liberate the gas. It's a key safety feature, and most cells have these. Now, pouch cells, the softer cells that you see in some things like cell phones, often these are pouch cells, they don't have the safety vents because they're not as rigid, and they can just bubble up if you generate these gases. So they're activated not by temperature, but by high internal pressure, and they help prevent rupture. The last thing you want in a pressure vessel, this becomes a pressure vessel, is a complete rupture. Then you have, that's when you have shrapnel flying around and a fast release. A vent is a more controlled release of the gas. The vent's main purpose is to prevent the rupture, but they also cool the battery. By releasing that hot gas, you're getting some of the hot stuff out, keeping it cool, and you also have isentropic expansion of what remains inside, kind of like when you pump or release the pressure from your bike tires. You can feel the temperature going up and down. Isentropic expansion cools the inside. So with 2 mechanisms, it cools the battery and gets rid of some of the flammable components. Now, the problem is that now you're venting out this hot electrolyte, which is flammable, and it's spraying, and so very often it does ignite and it burns outside. But still, it's better than the alternative of having a possible rupture. Almost always, when a battery vents, when the vent goes, it's a moving part, and you can see the vent disc that lifts up. It actually breaks the electrical circuit. So it's also built designed to break the electrical contact. And also, if there's some kind of an overuse of over demand for electricity, to break that. Okay, so these are safety vents. And the next, so there are several different safety features. First one's safety vents, and you can see that right here. The second is called current interrupt. And current interrupt has several different ways of happening, but there's a picture on the right here where it's basically a polymer that gets, when it gets hot, it melts and it breaks the circuit. It's kind of like a circuit breaker in your house. It's thermally activated, positive temperature coefficient that stop the cell current when the temperature increases. It's not resettable, so if your current interrupt or your vent activates on a battery, the battery is toast. You need to replace the battery. The next kind of current interrupt, I guess there are 3 different kinds that are shown on this screen, is called a shutdown separator. So remember, the shutdown is that polymer to make sure the cathode never contacts the anode electrically. If a battery gets hot, that stuff will melt. It's polyethylene, polypropylene. It definitely gets hot enough to melt. And if it melts, now the cathode and anode can touch each other, and suddenly you release all the electrical energy in a millisecond. So what they do with the design is have what's called a shutdown separator. And it just basically, in that polymer, it makes it 3 layers of polymer. Polyethylene, which melts first, 135 degrees C. And so the polyethylene will melt and then plug the holes and so the lithium ions can no longer transport across, and it stops the electrical current. So it's a second, well, I guess it's a third way. There are three ways that batteries stop the current flow. The first way is if there's a venting, the vent automatically breaks the electrical connection. The second way is this PTC, which is a little piece of polymer that melts and opens the contacts. And the third way is the shutdown separator. So when the separator, this is polymer, gets hot, it melts and closes the pores. And then the CID, current interrupt device, this is actually what's inside and activated when there's a venting event. Now, a battery like this isn't really going to get you very far if you have a heavy vehicle. So what they do is they wire them up in series and parallel. Generally, they're working with about 600 volts. Now, that's a risk to firefighters if they're using the jaws of life and they want to cut into the floor to rescue somebody, cut into the roof. They want to make sure they're not hitting a 600-volt cable. They need to know how to turn these things off. There are lots of hazards for emergency responders with electrical fires. There are lots of hazards with gasoline vehicle fires as well. But anyway, these get wired up, and they're discussed in terms of three different units shown at the bottom. The battery cell, this is an individual cell. And by the way, if anybody wants to come look at it after, I'm happy to share. The battery module, where in this case it looks like they've taken about 20 or 30 of these cells and wired them up. And then if you combine a bunch of modules together, you build that into a battery pack. And so that's covered by the first bullet. You got a cell, a module, and a pack. Some Tesla battery packs have 8,000 of these cells, 8,000 NCA 18650 cells. Can you imagine that? You get tremendous performance from these cars because you have 8,000 of these little guys, all underneath the floor. So an additional safety feature that's included in these modules is called a thermal management and a battery management system, TMS and BMS. And these are just like little microprocessors that monitor the temperature of each cell and the current of each cell and the state of health. It's like a computer system that makes sure your battery is not overheating, not overcharging, and helps protect you. In the case where you do have a module or a battery pack that's controlled by an external management system, some of the safety features are actually removed. So some of those safety features that I talked about, by the way, when you buy an individual cell, you get all these safety features. Let me go back one screen. You get the vent, but also the PTC and the shutdown separator and the CID, which is part of the vent. So basically you get 4 safety features. Anytime you buy an individual cell, you can buy these on Amazon. But once they put them, every safety feature has its own drawbacks. It's going to add weight, going to add cost, and you might have false activation. So when they start making 8,000 of these into a vehicle, they sometimes start taking some of those safety features out of the individual cell and then putting it into the BMS, this battery management system. And I'm not saying one way is better or worse. I agree it's not good to have too many safety systems. That can actually make things sometimes more hazardous. But I do think more research is needed, more needs to be done, maybe even accept a little bit lower performance until we can protect better against battery fires. So there are 3 ways to trigger a lithium-ion battery fire. There's thermal abuse, electrical abuse, or mechanical abuse. So in thermal abuse, if you put this in an oven, for sure, you turn on your oven at temperature to make a pizza or something, you pop it in there, for sure, it's going to get hot and it's going to go into thermal runaway. Whether it's state of charge of 100, state of charge of 0, that it's going to vent and you're going to have a little fire inside your oven. So that's thermal abuse, overheating or fire exposure. And the thermal abuse can happen just from one cell going into thermal runaway in contact with its neighbor. The second way is electrical abuse. Now, with all the safety features built into this battery, you cannot electrically abuse it enough to make it catch fire. So you can charge it up to 100% state of charge and short out the 2 terminals, and there are enough safety features in there that it won't go into thermal runaway. The vent may occur, but Before that, I think the other shutdowns will occur and it won't overheat. But out of these three choices, thermal abuse can make it explode, and mechanical abuse can as well. If you put this in a clamp and a vise, if you smash it on the ground, or if you pierce it with a nail, any kind of bending or sharp penetration can cause it to go into a thermal runaway. What happens is the cathode contacts the anode. Now all the stative charge comes out instantly. You have sparks and flames, and basically what you see here in this image with someone electrically abusing a battery and causing this big fireball. Okay. So if you take this battery, this is pretty new, and you want to do one of these experiments, make sure you're far away from it. And what I understand is that there's no amount of electrical abuse that will make it explode. But if you put it over a fire or over a heater, then you can reproduce this fireball that's shown there when the safety vent goes. So I mentioned a couple times thermal runaway, and when you talk to people who work on these fires or investigate them or design the cars, sometimes they get confused. Thermal runaway can mean different things. For example, it can mean one cell is hot, and so that heats up the other cell, and that catches fire, and that leads the other cells. Some people call that thermal runaway, but really, I think what's becoming a more accepted usage is that thermal runaway is when one cell by itself heats up to the point where basically it can't cool itself down anymore. Thermal runaway is when the heat generation outpaces the heat loss. And a really nice way to think about thermal runaway is this Semenov plot. And most of us who have had a combustion class, a graduate course in combustion, have looked at this Semenov type of plot. So the x-axis here is the temperature of the battery. So the temperature, assuming the battery is at some isothermal temperature, so increasing to the right. And on the y-axis is the heat release rate, so the internal heat production. So it turns out batteries, the heat release rate kind of has an Arrhenius type of behavior shown by that curve 4. So it looks like an exponential increase sometimes as you double the temperature, you'll have 10 times the heat release rate. But basically the temperature of a battery follows that curve 4. Low temperatures, you have no heat release rate, but as the temperature goes up and up, you get Arrhenius increase in heat release rate. So that's curve 4. The heat release rate inside the battery as a function of the battery's temperature. And these straight lines, the 1, 2, and 3, these aren't the temperature of the battery, they're the temperature of the surrounding gas, so the air that's near here, where 3 is the situation of the battery in an oven, 2 is the situation of the battery in, not as hot as that, but still hot. And 1 is what we have in this room. Luckily, this battery is in a safe condition. It's at condition 1. So condition 1, nice cool room, 22 degrees, and the Arrhenius curve has 2 intersection points on the Arrhenius curve, on the Semenov curve, intersection E at the lower left and F at the upper right. So right now, we're in a safe state. Where line 1 intersects curve 4 at point E. It's nice and stable. If suddenly this battery starts getting a little bit warmer, it'll move to the right, and the heat loss, just the convection coefficient times the temperature difference, will cool it back down. It'll go back to that intersection point E. This is a stable point. Right now, it's nice and stable. But there is another solution here. If we heat this battery up and it goes to point F in quasi-steady state, now this is unstable. If briefly it increases a little bit to the right and the temperature of the battery increases, now the heat loss to the surroundings can increase at the same rate and it will go into thermal runaway. But what's even worse is curve 2. Because if the room temperature now, say it's 100 or 150 degrees C, the battery will warm up to that temperature, and there's one intersection point here at intersection point D, but this is unstable. And this intersection will always lead to thermal runaway, and you'll go to an explosion. And then, of course, the curve 3, if the room temperature is even higher, then there's not even an intersection, and you'll go right away to thermal runaway. So I think I've explained this okay. There are two temperatures that you can get out of this plot. T2 is the self-accelerating decomposition temperature. So the ambient temperature, if you put this battery in an oven, you slowly increase the oven, kind of like the cup burner test. At some point you get to T2 and the battery will go into its own thermal runaway. And then TNR is the battery temperature of no return. So there are two things here. You can see the highest safe ambient temperature and the highest safe battery temperature. Okay, on to the next one. When these batteries burn, usually they just vent all their contents. When the vent goes, usually it's hot enough and it's still burning, all the electrolyte goes out. And with that electrolyte, remember there's salts. You need lithium, and these salts need fire retardants that may have fluorines in them, and you release some real toxic gases. A lot of people, this is kind of a secret. They don't want to, it's a trade secret. They don't want to tell the world what they're putting in their batteries, so it's a little bit hard to know. But lots of researchers have tried to measure, and they find that these things release oxygen, that's fine. But here's our friend now, HF, again released, carbon monoxide, hydrogen. So the last thing you want is a jet of hydrogen, oxygen. Of course these are going to burn, self-ignite. Methane and other hydrocarbons. In addition, there are metals in here too that get released. So the electrolytes include salts, always with lithium, but those include phosphorus, fluorine atoms, chlorine, arsenic is shown there. So depending on what the salt is, there's some nasty metals and compounds that come with that. And when heated in these salts, most of the F becomes HF. We saw that yesterday, that HF is very toxic. And finally, if you burn an entire electric vehicle, you can expect to produce about a kilogram of hydrofluoric HF. So nothing good comes out of a lithium-ion battery fire. We do some of these experiments in our department, and we're so careful that the vent is working well, none of the gas comes into the room. But even after it's burned and it's cool, you have these toxic battery cases to get rid of, and it's difficult working with these. So I tried to do research and to understand how much heat is released when an 18650 battery like this burns, and it's not very easy. So the best plot I can find is from 2020 here, Sun et al., where it's a plot of the energy that's released versus the battery state of charge. And if you look down at the bottom here, state of charge of 100 and the blue diamonds, you can see really it's the only data that's nice and linear. So for a state of charge of 0, of course, there's 0 electrical energy. For state of charge of 100, it's somewhere around 30 kilojoules. So that's a nice straight line. But all the other lines really have huge uncertainties and need to do hundreds of burns, I think evidently more than they were able to do to get good statistics. So there's the thermal runaway energy, which seems to increase with the state of charge, and then the flame energy that also seems to increase with the state of charge. But it's not too clear from this plot, but in other sources what I found as the last bullet is when a cell like this overheats and burns in air, the heat release rate contributions are about 70% from combustion, so burning those electrolyte oils in the air, 20% from the stored energy, and about 10% from anaerobic reactions inside the battery. So even if you have this battery in a nitrogen environment, when it has thermal runaway, it will still liberate 30% of the total heat. So it's a lot of energy that's packed in. You want to have electrical energy, but then when there's thermal runaway, it can be extremely hazardous. Okay, and thermal runaway can even occur at a state of charge of 0. So even if you deplete all the electrical energy in this battery, there's enough oxygen in the cathode that it can react with the electrolyte and go into thermal runaway, release the safety vent, even when it's discharged. But of course, the fire is much worse at 100% state of charge. This is a video performed in our department and done by Stas Dolirov. He shared it with me for this talk, and hopefully it will work better than some of yesterday's videos. So what happens is that it's 6 of these 18650 batteries, and the front one in that pyramid, he overheated. It's a state of charge of 100%, overheated it with an electrical wire, and then watched to see if that would propagate to the other batteries. And sure enough, it did. One battery burns, and that ignites the 2 behind it. And as those 2 burn, you see all these sparks and violent eruption, and then the 3 batteries behind that burn. So let me play that one more time. The first thing you see is that kind of gray smoke coming out. That's the electrolyte that gets hot in the safety vent, heating up. Then that ignites, and you get flaming, and it goes out, but it's too late. It's already heated up the 2 batteries behind that. Again, having this white smoke coming out because their safety vents have vented. And again, this starts flaming because it's hot and it's in the presence of air. And then the flame really increases the heat release rate until the last row, those last 3 batteries, all vent. And you can imagine if you have a vehicle with 8,000 of these cells and you just load it up on, fully charged, that if this propagates to all the cells, which certainly can happen, then it's quite a nasty fire. And not only that, but it's a fire that's not accessible like this. A fire in this situation, you could spray water on it. You would be able to get the water on the batteries. But in electric vehicles, the batteries are protected from rain and snow, and very hard to get water in where you want to suppress them. Some similar studies have been done by UL, formerly Underwriters Laboratory. They were really concerned about the micromobility devices in New York City. You can imagine in New York City, if you buy some of these electric bicycles are $5,000. The electric scooters, even more. Electric skateboards, expensive. I guess this one, I think, I don't know if you'd call that a scooter. Anyway, a little moped type of thing. And in New York City, you can't really park it outside. It'll get stolen. You can't charge it outside. So what do? Well, at night, of course, you bring it into your apartment and you plug it in and you charge it. No one steals it, and it's ready to go the next day. But there have been so many fires, especially in New York. There have been so many on my campus, at University of Maryland, that no micromobility vehicle is allowed in a campus building. At Princeton campus, you're not allowed to ride these anywhere in the central part of campus on the main sidewalks. There were so many collisions. There's so many of them. So really, the use has exploded, and now the vehicles also are exploding. The regulations are trying to catch up with the use. But in New York City, it's especially bad. In 2023, there were 18 fatalities, 150 injuries, and 268 fires from micromobility devices. So what they did is they took these electric scooters and they burned them by applying 157 volts to the battery pack with the battery management system bypassed. And they got fires like this. So they did it inside a scale apartment with furnishings and carpeting and watched the fires. And the videos are available online. Anybody can go look at these. They're published in 2025. And some of the initial blasts were strong enough to break doors and windows. And the fireballs were 2 meters in diameter, big fireballs like shown here. And in small rooms, they got flashed over in 1 minute. So the reason New York has 268 of these fires is because they have 1,000 times more of these vehicles plugged in. It's hard to do an experiment on that without bypassing one of the safety features. So they bypassed the battery management system, and they were able to reproduce these fires. But you can see how hazardous they are. You can also see how hard it is to think of a solution. It's New York City. It's a fast way to get around, but it's also a place where there's a lot of theft, and you can't charge it out on the street. So I don't know what the solution is. I guess the solution needs to be that more research is needed, and the manufacturers maybe need to sacrifice a little bit of performance in order to improve their fire safety. Here is a picture of a fire that occurred in Seattle. You can see here it's a T on the front. It's a Tesla. So the car was parked, and people noticed this kind of white fog coming out of it. So what is this? This is 18650 batteries that have overheated and vented, but it hasn't started burning yet, and it's venting these white clouds. So that's basically the electrolyte, these oils, basically oil aerosols venting out of the vehicle. And after that, I don't recall if it did catch, if the vehicle caught fire, but I would expect with that amount of release of the electrolyte that it did catch fire. And then you can see in the vehicle image at the right that the fire service came and they sprayed a whole mess of foam on it. It's not snow, but all around the vehicle, that's firefighting foam. And the batteries are still smoking. So it's really difficult to respond to these fires. The firefighter there, for sure, he's not wearing a scuba gear. I don't think. So they may be breathing some of this toxic products of combustion. So it's a problem. It's a problem for training the firefighters, for responding, and as I said, for getting the water to where the batteries are actually burning. Okay, so these fires are deep-seated, as the bullet said. Some have been put in an impound or in some kind of a lot, and they reignite days after suppression. And I've heard firefighters say the only way to be sure the fire goes out is to throw the whole car in a swimming pool. Okay. So this is my summary slide, and as expected, I'm a few minutes early, almost 20 minutes early. But these lithium battery fires are an increasing global problem because there's an increasing demand for them for the performance and the number of vehicles and phones and laptops. But more research can help. And here are about 5 different areas where I think more research would be helpful. A lot of these came from a 2019 review paper by Wang. One is to perform large-scale fire tests, and we're starting to see these, and associated computer simulations, and also associated firefighting to understand the best way to respond. The codes and standards probably aren't keeping up, and maybe they need to be tightened a little bit to improve the fire safety of these vehicles. Perhaps one good solution is more thermally stable cells. Maybe by more research, we can find some way to make these cells safer, less flammable, and less toxic chemicals that are emitted. Now, there's always trade-offs with that. There will be a trade-off in cost or trade-off in performance, but I think I'm on this side of favoring a little bit lower performance and a little more fire safety. And no matter what you do to make the contents less flammable, we always want to have more electrical charge there. And so, there's no getting around that there's always going to be a lot of electrical energy here that could actually start a fire, no matter how safe the electrolyte and the cathode are. Maybe the battery and thermal management systems need to be better. Maybe there needs to be better insulation between the cells so that if one goes into thermal runaway, it can't spread to its neighbor. And of course, we need to improve risk assessments. And with that, that's the end of my seminars, my 3. Thanks for being here all the way till the end and for being such a friendly crowd. It's been an excellent week for me. I hope you enjoyed Princeton as much as I did. Thank you.